Hello, abstract algebra students. This is the second lecture in chapter 1, and today we are going to talk about the closure property. We have already seen three other properties in the first lecture: the commutative, the associative, and the well-defined properties. These three properties were all properties of operations. Our fourth property, the closure property, is a property of a set. It has more to do with the set than an operation. So the definition is this. We will again suppose that both S is a set and star is an operation. Now, we will define what it means for the set to be closed under the operation. We phrase this as the set S is closed under the operation star. Notice that this is a little bit different in phrasing from the first three properties. Sets are closed under operations, whereas operations are commutative, associative, and well-defined on sets. So S is closed under star means for every pair of elements A and B, if both A is a member of the set and B is a member of the set, then A star B is also a member of the set. So closure means anytime you combine two elements in the set with the operation, the result A star B is in the set. And implicitly, this means that A star B must be defined as well. Now, let's practice our negations to begin with. If this is the definition of S is closed under star, see the definition of S is not closed under star, take a minute and think about what it should be as I type it in. S is not closed under star. Well, we have a for all statement, so we know from foundations, when we negate a for all statement, it becomes there exists. So this is going to begin with there exists elements A, B. Now we have to negate the predicate, which is an if-then statement. So there exists elements A and B such that all of the if part and not the then part. So all of A is in S, B is in S, and A star B is not in S. Okay, let's do a couple of quick examples with this definition. My first example, which I will accept without proof is true, is an axiom, is that the set of real numbers is closed under addition. Now, what this is saying is If both A is a real number and B is a real number, then A plus B is also a real number. Anytime you add two real numbers together, you get a real number. This is something we can accept without proof. Now, not every subset of a set that is closed is closed. Okay, to show this, we're going to claim if we take the set of non-zero integers, if we take z star, the set of non-zero integers, is not closed under addition. Now, this actually does require proof. While for all the familiar sets and operations, we will accept the ones that are closed or closed as axioms, to prove something is not closed does require a proof. So let's think about what we want to show here to begin with. Remember, using WTS as the abbreviation for want to show. If we take the definition of not closed and apply it to the set Z star and the operation addition, we want to show that there exist elements AB such that all of A is a member of the Z star, B is a member of Z star, and A star B, which in this case would be A plus B, is not a member of Z star. Now, to prove this, because we are asked to show that two integers, non-zero integers A and B exist, we get to choose A and B to be whatever we want. But we need to choose carefully. We need A to be a non-zero integer, B to be a non-zero integer, but A plus B to not be a non-zero integer. So I'm thinking, what are two non-zero integers that add to 0? Let's choose A equals 1 and B equals -1. Since we know that 1 is a non-zero integer, it follows that A is a member of Z star. Since we know that -1 is a non-zero integer, it follows that B is a member of Z star. However, since both word can be temperamental, since both A plus B equals 1 plus -1 equals 0, and 0 is not a non-zero integer, we may conclude that A plus B is not a member of R star. And this ends the proof. Now, what we have done here is we have put 4 sentences in the proof, 1 sentence for each of the phrases in the definition of not closed. We want to show that there exists A and B, so our first sentence is to choose A and B. Our second sentence is to argue why A is in Z star. Our third sentence is to argue why B is in Z star. And our fourth sentence is to argue why A plus B is not in Z star. I cannot stress this enough. Memorize the definitions, because the definitions provide roadmaps to how you need to write the proofs. More to follow.